So what do we do with the pyruvate that we get from glycolysis? What we're going to do is we're going to feed it into the Krebs cycle. And this is where we're going to completely oxidize that carbon compound and get as much of that energy as we can into NADH or FADH, a new electron shuttler. So we want those high energy electrons, we want that reducing power to feed it ultimately into oxidative phosphorylation. So again, little review, glucose is in the cytoplasm. Glycolysis, a whole series of enzymes, is going to break that down, produce some NADH, a little bit of ATP, and pyruvate. 2 molecules of pyruvate per molecule of glucose. And those pyruvate molecules, those 3 carbon molecules, are going to be now targeted to the mitochondria. Now, the mitochondria, again, remember, is our organelle, our powerhouse of the cell. It's going to make ATP. So this is kind of the first step of getting fuel into the furnace, literally. This is where we're burning it, oxidizing it. Now, the first step to actually get the pyruvate into the mitochondria is called the transition step. And in the transition step, we're going to bring in coenzyme A and make a compound called acetyl-CoA. So here's our pyruvate. See, there's our 3-carbon pyruvate. And this is where we're going to basically oxidize one of those carbons, and we're going to get CO2. So it's completely oxidized. That's why you breathe off CO2. This is the byproduct. In that process, we're going to generate yet another NADH, high energy electron shuttle. In the process, we're going to combine the remaining 2 carbons with coenzyme A to make acetyl-CoA. So this is what coenzyme A looks like. Just so you know, that's what it is. We're going to feed that into the Krebs cycle. This is also known as the citric acid cycle or the tricarboxylic acid cycle. Now, from one turn, we're going completely through the process. We're going to get another ATP, 3 more NADHs, and 1 FADH2, which is just another electron carrier of a slightly lower reduction potential. So again, now we're in the matrix of the mitochondria, and we're going to go through the citric acid cycle. Now, the citric acid cycle is going to again start with acetyl-CoA and feed into the cycle. It's called a cycle because the products of which are going to feed into, combined with acetyl-CoA as the first step. So the last product is going to feed into the first product to make our wheel start to turn. So let's take a look at that. So it has 8 steps, and oxaloacetate is our final product, and acetyl-CoA is our first product, so we're going to form those together to make citrate. I do want you to memorize every step in the TCA cycle, or the citric acid cycle. We'll go through each at a time now. So acetyl-CoA is going to combine with oxaloacetate to make citrate. Right? Now you can follow the carbons by looking at the 2 red carbons, and really it's the 2 carbons from the previous turn of the cycle that are going to be oxidized this time. So citrate then is converted into isocitrate. So we have acetyl-CoA, citrate, isocitrate. Isocitrate is converted to alpha-ketoglutarate, and in that process we generate high-energy electron carrier, NADH. Again, that's powerhouse. It's like a little battery. We're waiting to shuttle it over to use it to make ATP. We're going to give off one of our carbons at this point. Now, after alpha-ketoglutarate, we're going to convert that into succinyl-CoA, and that then will generate yet another NADH. Succinyl-CoA is converted into succinate, and in that process, we're going to go through a GTP intermediate, but we're going to make an ATP molecule. Each of these steps has been simplified. There's an arrow here and a lot of little swoopy arrows, but literally some of these steps have more components involved, but these are the major intermediates in this process. So again, acetyl-CoA at the top to citrate, isocitrate, alpha-ketoglutarate, succinyl-CoA to succinate. Succinate to fumarate is going to produce our first FADH2. Again, this is just like NADH, except it's a slightly lower redox potential, which we're going to see. We're going to feed it into our electron transport chain a little bit later down the line, but we'll see. It's another electron transport carrier. We want to think about that. Fumarate is then converted into malate, and malate finally is converted into oxaloacetate, and that generates our last NADH. So we've got 3 NADHs on the board, and 1 FADH, and 1 ATP. The electron carriers are going to be what we're going to be interested in following now. Those are going to feed into oxidative phosphorylation or electron transport to generate ATP. ATP generated at substrate level, as we see here, is ATP ready to be used. Now, the trick to remembering all the intermediates in the tricarboxylic acid cycle or the citric acid cycle, at least the way I remember it, is a car in Kansas stops slowly for more oil. Acetyl-CoA, car, citrate, in, isocitrate, Kansas, alpha-ketoglutarate, stops succinyl-CoA, slowly, succinate, for, fumarate, more, malate, oil, oxaloacetate. If you can come up with your own mechanism to memorize that, by all means do so. That's how I remember it, and I wanted to share that with you. So again, transition step in the Krebs cycle is going to yield 2 ATP, ready to be used, fuel for the cell, 6 NADH, right? That NADH is high energy electrons ready to roll, and 2 FADHs. So remember, we had 2 pyruvates to feed in, so now I'm going back and summing from 1 glucose molecule, right? So I feed in 1 pyruvate, I get 1 ATP, 3 NADHs, and 1 FADH, but from that 1 glucose, I got 2 pyruvates. So now I've got twice as much of that yield, right? We also give off our 3 CO2s in this process. So we've oxidized completely the carbon-carbon bonds, and now that's the waste product that we breathe out from the cellular respiration that we do.